Very good afternoon to all of my dear fellow presenters, many esteemed judges, and my dear co-authors. I, Shobhani Bharti from Sister Nivedita University, am delighted to represent my team of authors and from Sister Nivedita University itself. I am Shobhani Bharti. We have Shobhana Banerjee, Shiva Mandal. We have Saurabh Kumar Ghosh, Professor Saurabh Kumar Ghosh, Professor Shani Mondal, and Professor Ondiban Mithro as our mentors or guides. Our concrete statement or our topic of work is basically HCAT-Net, a novel hierarchical cross-attention transformer network for balanced, enriched ordinal laws, which is a novel model or architecture proposed for EEG signal, emotion identification or classification. Yes. So, as we know, EEG signals or electroencephalography signals are a key. It's a key signal which is we receive that from the brain, which represents mental health. It is key for adaptive computing. It represents real-time emotions, and it is extremely important in computational, especially advanced computational and biotechnological systems. So the pretty much importance of EEG signals lie in the fact that it is non-invasive, it is real-time, it is portable, especially with nowadays wearable EEG watches and signals and stuff like that. It's not as intensive as it used to be essentially, and also it represents a rich emotional indication of the person's mind, which is not possible otherwise. There are a few challenges that I would like to speak about when we're working with EEG signals. As one of the previous authors also pointed out, EEG signals are extremely high dimensional signals. That is a primary concern when we are working with machine learning or deep learning models. Also, EEG signals, essentially most of the models that work with EEG signals do not have a natural order, especially when we are working with loss functions. They do not consider a natural order for the loss function. So, for instance, if we have positive, neutral, and negative as the three respective emotions, most approaches, or I would rather say all of the current approaches, treat these three as completely separate classes, and there is no continuity or there is no relation amongst these sort of classes. So we decided to fix that, we decided to work on it, and we came up with a balanced ordinal loss function, which essentially not only penalizes when you're getting the class wrong, but also penalizes more if your mistake is more on the scale. So for example, if your model is supposed to predict positive and it predicts negative, it will be penalized much more than if your model is supposed to predict positive and it predicts neutral. So it gives a much wider range of understanding with respect to the loss function to the model. And also we have kept the original loss component, so that's not completely absent. It's just present in a much more complicated fashion, which we'll discuss in the upcoming slides. Right. Before we get started on the proposed model, I would like to just discuss in short about the current approaches that are used in EEG emotion classification. So, as you see, there are the earlier approaches, which are the traditional classifiers or traditional models, which obviously are very inefficient as a matter of fact, because they essentially require manual feature extraction, which is quite difficult, especially in higher order data such as EEG signals. So, later after that, when deep learning came in, LSTMs as well as bi-LSTMs as well as CNNs were used very extensively in these sort of signals, and hybrid models such as CNN LSTMs and CN LSTMs, CNN, other a lot of multitude of approaches were used to basically get a good result while balancing the efficiency of the model, so the size of the model as well. So the most recent approaches were GNNs, or graph neural networks. These are extremely advanced in the fact that they use graphs to represent the complicated EEG signals. But the main issue of GNNs and the previous approaches is the fact that there is extremely limited scope of parallelization. There is absolutely no temporal order, which I previously discussed as well, and the fact that there is no generalization ability of the previous models, especially for GNNs. So, to counter all of the discussed problem statements, especially these three problem statements, we have proposed a model. So, again, before just going into the model, the dataset section needs to be discussed in depth. So, the dataset that we used has a special significance. There are pretty much 4 datasets that are typically used for EEG classification, emotion classification. So the first one is DEAP dataset, which is dataset for emotion analysis using psychological signals. The second one is SEED dataset, which is SJPU, emotion EEG dataset. The third one is DREAMER, and the fourth one is EEG brainwave dataset, feeling emotions. The reason why we use this dataset is quite simple. It has got 3 classes instead of the typical 2 classes, which is positive and negative. The reason why we chose this dataset is we have to ensure that we can show the capability of our model and the capability of the loss function, the proposed loss function, which greatly enhances the results of the model. So this is the reason we chose this dataset. The details of the dataset are quite evident. There is 2132 data points, and it was collected from 4 young adults with a 4-channel induced EEG headband, and the data was generated by showing different sort of videos to the users, to the subjects, and then their EEG was generated, and then that was based as a matter of fact. So this is a completely time series data set using this for the model. Let us discuss what the model did now. So our model is quite advanced. So initially we are using 1D residual network for the first layer. So there's a block system. So initially we use 1D ResNet block. So I'll be discussing right now what one block consists of. So one block consists of conv1D plus batch norm plus value activation function, and then we are using a residual skip function. So essentially this whole attribute of this whole 4 pillars complete one residual net block. After this, use max pooling for downsampling of the EEG signals, and then the output of the first 1D resonant block is essentially a hierarchy of time series which serves as the transformer stage output. Now coming to the second stage, this is the transformer stage 1 and the transformer stage 2. These work in parallel. The first stage of the transformer network. So the stage 1 is a stage that takes the whole sequence, the full sequence, and then it captures the local or the low level, the fine-grained patterns of the EEG signals. That is the work of the stage 1 transformer network. And the stage 2 transformer network does the complete opposite of the stage 1 transformer network, and the fact that it tries to capture higher level representations or patterns in the data. So this ensures 2 things. We are not missing out on any higher level or lower level representations in the data due to this 2-stage transformer architecture instead of the typical one large transformer architecture. Also, we are ensuring parallelism. So after these 2 transformers are used, we fuse this using cross-attention fusion. So cross-attention fusion essentially it just fuses the 2 layers, which is the fine and the coarse representations coming from the 2 transformers layers. These cross-attention fusion was used because it is an advanced module that prevents any sort of information loss, because that is extremely crucial when we are working with these sort of data sets. And at the end, we use a balanced ordinal loss as the loss function, which we'll be discussing later. One thing I would like to point out is the fact that we've used rope embedding. So what is rope? Rope or rotary positional embedding is a completely new and advanced embedding technique used in the transformer architecture, which very specifically has we found to be working incredibly well for EG signals. So rope was introduced in the paper. The name of the paper is Reformer Enhanced Transformer with Rotary Position Embedding. This was written in this published in 2024 actually, quite recent work. And this was we used this because of a couple of reasons actually. The first, pretty much the main reason is the input to the transformer layers. There's a set of tokens, right? But the problem is there's no inherent it's just a simple set of tokens. There's no inherent order in the set of tokens. So that is quite problematic when we're working with time series data, especially like EG data for instance. That is something where we use rotary matrix, which is used to basically store the exact point of the location of the data point in that set. So we use a rotary matrix or rotary embedding, and that is how rope is used. If I have to use a complete sentence to just summarize it, is because it improves the awareness of the temporal structure inside attention module. So that is why rope is used. And after that, we pass it to the cross attention fusion and then pass it up to the balanced ordinal loss. So this is the architecture that we discussed right now. Then initially, as you can see, there's a residual network block, there's max pooling, and there's point-to-point projection layers. The second part, after the greenish part of the architecture, it actually consists of the first transformer layer, and the third, after the gap there, after the small green part there's the second transformer stage. We fuse it together, and after that, we use there's a classification head at the end, which uses a combination of fully connected layer, FC layer, and then we basically predict the three classes, which is positive, negative, and neutral. This is the architecture that we used. This is a complete breakdown of the first feature extractor layer. This is complete detailed logs that I used.
Come to the results.
Yeah. So, is it okay if I discuss the loss function? It's okay. So, the model we have tested, we use 5 different advanced models as the baseline. The first one is NLP, the second one is base CNN, the third one is CNN LSTM hybrid, and the fourth one is resonance style CNN, and the sixth one is obviously our approach, which is HCAT-Net. As you can see, the output is quite, it speaks for itself, it's quite advanced, it's quite good. And we trained it for 250 epochs, 260 epochs, I think. And the value for the balanced ordinal loss was alpha value was 0.5, so there was a good balance between the cross entropy loss and the scaled ordinal MA component. So, the balanced ordinal loss function that I should just maybe just one line about. So it's just as I discussed, there is 2 components to the loss function. The first one is the very standard cross entropy loss, and the second component of this loss function is the scaled ordinal MA loss, which is multiplied by a weighting factor, and then it's added to the original loss component, which gives a very good representation of the good, serves a very custom good loss function for this type of EG work. It's actually quite impressive how well this works. For the ablation study, we've discussed that without the cross-attention component, there's a 3.4% performance loss, and without the ordinal loss that we've used here, simply using a cross-entropy loss, there's a large amount of misclassification between emotions, which results in an accuracy of about 84 to 88%. So using these 2 special components, we've received I think 98-99% accuracy, which is quite impressive considering most of the works here go about around 92-93%, as you can see here. This is the loss function, loss graph curve. There's a small spike there, which suggests maybe some problem, but I don't think that will cause an issue. That is probably due to the adjustment of the module functions while the learning rate was being decayed. So So the conclusion is basically we have successfully implemented a completely novel architecture combining, we've got three pretty much three primary novelties in the work. The first one is the custom loss function that we've used. The second one is the cross attention component of the module that we've used. And the third one is integrating rope embeddings in this architecture. So these are the three completely novel things that we've done in an architectural sense, of course. In an architectural sense, and yeah, it had received 99.8% test accuracy. So there was no scope of overfitting in that module as well. And yeah, so the future work would definitely be, hopefully we can extend our model for more generalizable test cases, as well as we are hoping to introduce a distilled version of the model in the future as well. And the third one would actually be to test our model on multiple data sets and multiple settings, which would generally give us a very good idea if the approach is robust or not. However, I think the problem in this case is again impedance is extremely high dimensional. So there needs to be some kind of maybe PCA or PSA component before the model, so that we can test how that works out. So that is in the future scope of the work. And these are our references, without which we wouldn't have been able to complete this. And then thank you. I would really appreciate any questions. If there's a question.
So you have told me that you have it's a almost binary classifier. It's a positive
No,
or negative.
it's a multi-class classification. There are three classes: positive, neutral, negative. It's a multi-class classification problem. There are three classes: positive, neutral, and negative.
Look at your positive.
Sorry. So that's the reason the loss was. That's the reason we chose this data set, because the loss we had to introduce a generalizability into the loss. Yeah.
In the neutral section that you are saying, those I guess include the emotions that are neither positive or negative, like you cannot classify into one of those. But suppose there can be some emotions which can express both positive and negative. Negative in the sense like suppose if I say nostalgia,
Right.
it can be a mix of both happiness and sadness. So in these type of emotions, how are you going to classify into a single class?
So essentially, the data set that we used, we didn't generate on our own. So it was a completely standardized data set. So these are the data points that were already present. With respect to your question, I would like to point out that the seed data set, which is also another standardized data set that is used in this task, has so generally these EG emotion classification tasks have there are not four classes, there are four types of emotions which you just expressed right now. So there's anger, there's I think three other general classes, and then inside that we have to classify into two classes. So essentially, for though if we used a C data set for instance, we have to put four metrics. So accuracy for four different types of EG signals, right? So here, the reason again we chose this data set was just to prove that when we are using three or more classes, we can introduce a generally progressive sort of we can try to capture the relationship between class 1, class 2 and class 3 in a more effective manner, rather than treating the three classes as completely different components. So that's the reason we chose this data set. But then with respect to your question, I'm sure there probably would be more approaches or more data sets that we could look forward to in the future of the scope of the work. Thank you so much.
Have you done any cost validation? These are only 180%, 20%. Have you done cost validation of your?
Absolutely. So K equals to 5.
One question, you have used two class transformer, one for low level and high level. So what changes you have done in the transformer rope model?
So in the two stages that were used?
One is used for low features,
Yes,
and
yes.
one is the global features and the
Yes.
So what difference you have implemented so that you can catch only the low level features and another is the
Right. So the simple one word for that is a thresholding. So we use a threshold which would generally smoothen out the features for the low level transformer. Sorry, the high level transformer, which would be able to capture high level dependencies. So for instance, in the EG signal, for instance, if there's a small disturbance, a small sort of change in the signal in a small region, that would be captured more inherently, that would not be filtered by the threshold. So that would be captured inherently by the higher level, low level transformer.
So how you just set the
So
What is the technical basis? Within the transformer, it was
no, the architecture of the two transformers are the same, but the purpose is different.
How?
So we use
Things are same.
yeah.
Why are you predicting that this will take low level and this will take?
So that's the what's the threshold. We use this, like for instance, a smoothing sort of filter, if you imagine, sir. For instance, if you take a picture,
Threshold means actually.
yeah, greater than will take it and then lesser than will reject it.
What is that threshold?
Yes.
Is the amplitude?
Yeah, so as you can see, sir, the data is time series data. The data is time series data.
Level means is the window size. What part? What long part? What short part?
Yeah. So, sir, again, if the data is time series data, right?
Yeah.
So, for example, sir, we have amplitude, right? So, if we go above a certain amplitude, that stops becoming a low level amplitude and it goes into a higher level
So
amplitude.
that is one level.
Yeah.
Another level is there. You can observe the signal in short time duration. You can observe the signal.
So, sampling, yes.
So which one you want to take?
So, the first one, sir, we have not considered sampling in this work as of yet. Sampling can definitely be something that we implement in the later scope of work, but what we did was we sort of looked at the amplitude of the signal, and if it goes above a certain threshold, then we're considering it in the higher dimensional transformer layer, and then
in the transformer layer, is there any parameter where you can set the threshold?
yes, absolutely.
Which parameter?
So that's alpha, that's a parameter that we are setting. So if you look at this, I think this will be more clear or easier for you to understand. This one. So, sir, initially, the resonant block, the output from the resonant block is coming. We are processing it in two stages. Like the first output is going to the first transformer layer, and the second output is going to the second transformer layer. I think I said, sir, the first transformer layer receives the direct output from the resonant, and the second transformer layer gets the thresholded version of the output from the resonant, and it proceeds to use parallelism, process them together at the same time, combine them using a cross-attention module, and then send it to the classification, or to multi-class
You
classification.
are putting the threshold before the transformer.
Yes, absolutely.
So for another question then.
Yeah.
Why are you telling that that it will capture on the high level one transformer will capture on the high level, not low level?
So, sir,
Because it is getting both high level and low level signals. You are not using any threshold for that.
yeah.
So transformer is capable of capturing both low level and high level transformer.
Right.
Low level structures.
So, sir, basically, typically again, in these sort of architectures, one transformer to use. Like I said, one transformer aims to capture both low level as well as high level dependencies. What we did was the approach this takes is use a single transformer. So the problem with this approach is there is no parallelism, number one. Number two, as we
Why parallelism is required?
because of speed, inference time. No, sir, this is we are using two transformers parallel, so the inference time is getting half.
Since you are using two transformer parallelly, that means you are increasing the number of parameters.
Yes, that is.
Your model is becoming overloaded.
So, sir, there is a compromise between inference time and parameter count or the weight of the model. That is why that is also in terms of
the complexity of your model is increasing, so you should use some overfitting.
no, sir, the overfitting is not happening because, like I said, 99.8% was test accuracy. There is no overfitting happening. And more importantly, the architecture that we
Why overfitting is not happening?
so because we've used dropout, we've used max
It is observed in indicator machine learning systems. If you increase the parameter,
of course, sir, but that depends also on the type of data. The data that we are using, each student is inherently very good.
depends on the type of data.
Yeah, of course, sir. So if the data is very higher level data, then the model parameters should account for it by being a high parameter model.
Why do you get overfitting does not depend on type of data?
But sir, if the data is like a higher dimensional data, then the model needs to account for it by being
Data is higher dimension. The model is higher dimension here.
Yes, sir, because the data is also dimensional. That is why we are accounting for. Yes.
So if you are increasing the number of parameters, that means you are increasing the bias, right? Right? You are trying to, decrease the variation. But
Yes.
you are trying, but at the same time, if you are increasing the number of parameters, okay, to capture the nature of the data, so you are increasing the bias at the same time. So and also this is I am agreeing with sir, and also you mean threshold. So
Yeah.
if you just discuss this for a block in a window, so there is a low level and there is a
Yes, yes, higher level.
higher level. So which one you were actually this is not very clear.
So again, ma'am, after the output of the ResNet is coming, the first block is getting we are getting the downsampled output from the ResNet block. We are using that downsampled output directly in the stage 1 transformer, the first stage of the transformer with row, right? We are also taking the same output from the ResNet. We are using a threshold function on the ResNet, and we are cutting off the lower level representations. So we are only keeping the high level
Okay,
representations.
so you are
Yes.
taking out this higher level threshold.
Yes, so one, yeah.
Thank you very much. Just come to the first slide. I just take the photo. Okay, just.